Okay. So I'm giving my lesson on equal temperament and just intonation and why we use equal temperament, because I think it's important for us as musicians to understand why we do the things that we do and use rather than just blindly accepting it. And so, what is temperament? Different temperaments are different systems of tuning. So they're the different ways that we can split up the frequencies in an octave to get the different notes. The two most popular ones and well known are equal temperament and just intonation. Each of them have their issues that you can't solve, and one isn't necessarily better than the other. But as Western musicians, we use equal temperament. And equal temperament was created around 1639 by mathematician Marine Mersenne. And then just intonation has just kind of been around forever just because it exists in nature and that's how physics works, so it wasn't really invented. And so if we get into more specifics, just intonation is all based off of the overtone series. If we look, here I'm going to draw a little bit. If we look over here, we can see the overtone series represented as waves. And so the fundamental frequency is the first note of the overtone series. It can be any frequency that we want it to be. And so the rest of the notes come naturally after the fundamental frequency. And so this means that all the notes in just intonation have a perfect rational number relationship to the fundamental frequency. And if you don't remember your ratios from first semester music theory, I listed them over here because, yeah, who remembers those? So, for example, if we have the note A4, which we know has a frequency of 440 hertz, and we want to find the rest of the notes using just intonation, we can use these ratios to figure out the different frequencies of the notes. So if we want the octave of A4, which is A5, that is going to be the first overtone of the overtone series, which has a ratio of 2 to 1. So we can multiply our 440 hertz that we know A4 is, and to get A5 would be 880 hertz. And if we want to do a different example, if we want the fifth above A, which is 440 hertz, and E is a perfect fifth above A, so that ratio is 3 to 2, which is also the second overtone in series. So we can take 440 hertz and multiply by the ratio 3 over 2 and figure out that E has a frequency of 660 hertz. And so because just intonation is based off of the overtone series, it has a couple of issues. The main issue is that when you base all the notes in a scale off of one note, whenever you have to change keys, you have to change the entire tuning. So if you look at this, the biggest issue with just intonation is you have to change keys you have to change tuning every time you want to change keys. So if I'm playing a piano concerto that starts off in C major and then transitions later to A minor, I have to retune the entire piano if I want to stay in just intonation. And so, if we see here, these are the frequencies of the notes in just intonation in C major. We can look at C as A is 436.05 hertz. But if we're in the key of A minor in just intonation, A is 440 hertz. So that's why we don't use just intonation. It's because anytime a piece of music wants to change key, you have to change your entire tuning. Otherwise, your entire piece will sound out of tune when you're in that key. So just intonation only works in the key that is based off of the fundamental frequency that it's in. And so let's get into specifics of equal temperament. So equal temperament is what we use today, and it equally spaces all the 12 notes in the octave. So it does this by multiplying by the number, the 12th root of 2, which is a very important number in equal temperament. Equal temperament uses the number the 12th root of 2 because if you multiply the 12th root of 2 12 times, one for each note in an octave, you get 2. So that way, in equal temperament, the octaves are always exactly double the frequency. And so if we want to find, if we have the note A, which we know is 440 hertz, and we want to find B right here, each half step you multiply by the 12th root of 2 to find the frequency. So if I have the frequency of A, 440 hertz, and I want to get B, that's 2 half steps. So it's going to be 440 multiplied by the 12th root of 2 squared, 1 for each half step. And then, so you can do this all around. So if we have C, and we know the frequency of C right here, and we want to find the octave above it, we count the half steps all the way up, which is going to be 12, and then that would mean the 12th root of 2 12 times, so the 12th root of 2 squared, which is just 2. So the octave is always exactly double the frequency of the initial pitch. The biggest issue, even though we use equal temperament, it does have its issues. The biggest issue with equal temperament is that it's always slightly out of tune. And so if we look here, this is the frequencies of an A major scale in just intonation, and this is the key of A major in equal temperament. Just intonation is, I guess, perfect in the given key because it works off of the overtone series. But if we look at it compared to equal temperament, they're slightly off. For example, in the key of A major in just intonation, B is 495 hertz, but in equal temperament, it's 493.88. So it's slightly off, and as musicians, we can sometimes hear that. We're trained to adjust this, and most of the time, we don't even realize it. When you play in an ensemble and you tune chords across a group, you can you adjust your pitch so the chord stacks nicely and is in tune and consonant like it's supposed to be. But if we played it with perfect equal temperament, then it would be slightly out of tune. And so by doing this, you tune to the overtone series rather than equal temperament, which a piano is tuned to. A piano will always be slightly out of tune because it's tuned to equal temperament, where the frequencies are slightly off what the overtone series is, so they sound slightly out of tune. And so hopefully with this, you'll be able to understand why as musicians we need to listen in to the others playing around us. Even though our individual note can be in tune, we still have to adjust because as musicians we know that this close enough isn't good enough for us, and that in any given performance we have to be exactly in tune with the overtone series for it to sound perfect, even though we work in an imperfect system.